So I see motion, people moving their arms like this and this. Yes, what the shift register does is that if you look at the picture up there, as I'm showing over here, this value D1 shifts into D2 at the clock cycle when the clock goes, when the clock rises, and D0 goes into D1, and the new value goes into D0. So the new value is always 1. So D0 becomes 1, and then the old value shifts over here, and this old value shifts over there. Okay. So this continues. At time 2, we get a new 1 in here, and this value shifts here, and this value shifts here, and so on. 1, 1, 1, and then after that, it's all filled with 1s, and more 1s are coming in, so it just stays as 1 the whole time. Okay, so we've analyzed the up counter, we've analyzed the shift register. The final row here at the bottom is the comparator. So what the comparator is doing, we shift up here, is it's comparing the inputs coming into A and the inputs coming into B, and the value F is high when A is less than B. Right? So we need to determine when A is less than B. So this is the A and this is the B, based on the input shown here. So at time 1, A is equal to the number 1, and B is also equal to the number 1. Right? They're both 0, 0, 1. So A is equal to B. That means A is not less than B. So we get a 0 right here, right? Because in fact A equals B in this case. So if we go to the next moment, A is equal to the number 2, right? Actually, we know this is 1, 2, 3, 4, 5, 6, 7. A is equal to the number 2, and B is equal to the number 3. So A is less than B, 2 is less than 3, and so F is equal to 1. Okay, so we can continue in this fashion. Here we're comparing 3 to 7. 3 is less than 7. And actually, it becomes easy here, because remember, this is 4 and 7, 5 and 7, 6 and 7. So in every case, A is less than B, until we get to the end, where we're comparing 7 with 7. And those are equal, so F goes lower. A is no longer less than B. Yes? Okay. Yeah, I've been using this terminology of most significant digit and least significant digit. Let's think about decimal numbers, right? So, which year were you born in? You were not. Oh, really? 95? Okay. Okay. 1995, right? That's a number. It's a 4-digit number. If you were born a year later, you would have been born in 1996, right? But if you were born a millennium later, you would have been born in 2995, right? So you can see that the units digit here, this is third grade, second grade math, but the units digit here is less significant because it takes a few steps to change it, whereas this thousands digit is most significant. So when I talk about the most significant digit here being Q2, so our notation is that the 0 is the sub-0 is the least significant digit. The sub-2 is the most significant when we have 3 digits. So this is the one that changes most quickly. As you can see, as we count from 0 to 7, it flips every time. This one only flips every 2, and this one flips every 4. Just like this digit here changes every 1,000. Okay, so another question. Is there a question about PWM? Because we haven't talked about that. And PWM usually shows up as a combination of a counter with a comparison. So I don't have one off the top of my head. I could flip through. Does anyone have any question about that, or any other questions? Yes. Okay, sure. In fact, we have a counter here. Okay, so this is a counter. Let me draw, and we also have the times over here. So let me draw the clock cycle. Let me just draw over it. So remember that the clocks trigger on the rising edge, right? So if we have a nice even clock, it goes like this. Right? That's how the clock is going. And every transition from T0 to T1 happens at the rising edge. So it's got that frequency. The least significant bit, Q0, I can draw that picture just by following the zeros and ones. So it's low, and then high, and low, and then high, and then low, like this. Right? So the least significant bit has twice the period as the clock, because you can see its width is twice as much. One entire cycle of it takes 2 clock cycles. Right? So that's the least significant bit divides the clock frequency by 2. Frequency goes down by 2. So it's a frequency divided. The next one does it again by 2. Okay, so that's 1/4 of the original clock frequency. And then the next one is even slower. Okay, so that's basically the rule. It was illustrated by this picture. Yes?
If there's a load, and like the load can vary on and off, is the frequency divider not working anymore?
Yeah, it can be weird, and there are some. So that's if I can find one of those questions where that happens, that would be a great question to do next. It's exactly the kind of thing that I want. Yes.
And the down counter would be 1 0 1 0 1 0 1 0. It was a down counter.
Okay, if this was a down counter, then instead of counting, it would be as if we were counting in the time reverse direction: 7 6 5 4 3 2 1 0. And so you might, if I reverse time, it's counting 1 0 1 0 1 0 1 0, right, as you suggest. But only because we started at 7. If we had started at 6, for example, and gone in this direction, then it would count 0 1 0 1 0 1 0. Okay, but I think on a case-by-case basis, you should be able to derive that.
Can you do problem 2 on page 40?
Problem 2 on page 41, is that like a PDF page? Because I don't have.
Yeah.
So what is the reference number on it? Is that a PWM question? What is the? They each have like at random positions here. They have numbers that have been inserted.
41.
Oh, so it does say 41. That's this problem. Oh, that's almost the same problem. Okay. Shoot, not here.